In this video I'm going to discuss self-induction, mutual induction, and then transformers. So we know that a current carrying wire has a magnetic field around it. If it's creating its own field, it has its own flux. So the current changes, as in when the current starts to flow or decides to stop flowing when you press the switch, there is a change in the flux, change in the field, because there's a change in the current. You will have a self-EMF, self-induced EMF, trying to oppose this change as well. So that means, simply put, that when I start my current flowing, let's say in this direction and down the coil, because of this self-induced EMF, it will try to push back. It will be a bit slower. Eventually the current will become steady, and then the self-induced EMF will stop because the current is steady. Only when the current stops flowing, that's when you will have another self-induced EMF. The current is trying to stop and the self-induced EMF wants to keep it going. So this causes a small delay when you switch a light bulb on, or when you switch the light bulb off as well. So that's self-induction in the wire that carries the current. The faster the change, the greater the change in flux, which means the greater the induced EMF that will oppose this change. Okay? It only happens when it's changing. It doesn't happen when the current is constant. Because when it's constant, there's no change. So then there's no flux change, there is no induced EMF. Mutual induction is the same idea. If I have a coil on the left-hand side, and even if there's a space between the two, and I have a coil on the right-hand side, because of this change in flux when a current changes, for example, switching the current on and off, or using AC because that goes positive to negative, that will create a constant change in flux, change in field. That will induce a current in this side as well. It will be the opposite to the change. So if it's getting stronger, it will be getting weaker. It will, as in, if it's going, let's say, clockwise, this will be going counterclockwise. If it's going counterclockwise, this will be going clockwise. Opposite direction. Not too important, you just need to know that it will create a current. This lamp will turn on and off as this is changing. We call the first coil the primary coil. The second coil will be called the secondary coil. And this is the formation of a transformer, which we'll get to. If it's a steady current flowing, what's going to happen in the secondary current? Well, as you know, if my fingers are coming down the page, like this, if I take my fingers down the page, my thumb will be pointing to the right. However, it is constant. If it's constant, there is no change in flux, there will be no induced voltage. Nothing will happen. However, in example 2 now, I have opened the switch. That means the current will decrease. Opening the switch is breaking the circuit. The current will stop moving. So that means, in this case, we know that the current is getting weaker. That means the induced field will be in the same direction as we discussed using Lenz's law previously. So it will be in the same direction. The induced field was going to the right, as I drew in the previous picture, and that means the induced field will also go to the right. And again, in this case, if it is going to increase the current, we already established that the field is going to the right because the current is coming down. My fingers are down, my thumb is to the right. It looks like this. My fingers are down, my thumb is to the right. And we find that this is getting stronger, so it will oppose the change. It will be in just the opposite direction.